All right, so this is our second example problem where we're going to use centripetal force, which will help us tell us the direction of the net force and how much the net force should be. And then Newton's second law, which is going to tell us how to sum up the forces. So when we're doing these, we're going to use both. The two equations that we're going to use are going to be the acceleration is the net force over the mass. Sometimes said like this, force equals ma. And we're also going to use this one, that the centripetal force is mv squared over r. I need to check, it may be stated on your, instead on your equation sheet like this, that the centripetal acceleration is v squared over. That we got by looking at the virtual lab of items going in circles, and we found that the force was directly proportional to the mass, is proportional to the velocity squared, and it was inversely proportional to radius. And then if we use Newton's second law with this, we can get which part of this represents the acceleration. This is always going to be towards the center. So that's the key here. So when you have something going in a circle. All right, let's look at our example problem here. So this is the one that I did towards the end of class when we started running out of time. We have a roller coaster going through a dip in a track, radius 30 meters, speed of 20 meters per second. The velocity is going to be changing constantly because it's going around a curve instead of going in a straight line, even though the speed stays 20 meters per second. Rider in the car has a mass of 65 kilograms. Calculate the normal force acting on the student. So when you're approaching these problems, always, 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 always draw a diagram first. So this one has a dip in the roller coaster. It's going to look different for something going over a hill on a roller coaster. So here we go. We're going through a dip in a roller coaster like this. And this would actually be different for every single point on here. Let's do them at the bottom of the track because it's easiest to figure that out. All right, so here we go. They're in here. If I continue the circle around, my curve should have a radius of 30 meters. And I need to figure out what forces are acting on this person who's here. Oh, here's the rider, right? So here's the rider in the car. Really, this would be the force of the car on the person in here to make sure that they're like staying in the car. All right, here we go. So our free body diagram is going to look like this for the person in the car. I'm going to have the force of gravity. And I'm also going to have a normal force. Now, for the normal force in this situation, I need to look at what's going to be the direction of net force. I can't draw. I'm going to draw this like this. Here's my normal force. But I can't say which of these two forces is larger until I look at which way is towards the center. So I look at this and I say my centripetal force, aka the direction, the amount of force that's available to push me towards the center is going to be in the upward direction, which means that this has to be greater than mass times acceleration, right? Or I could, if I drew this, this should be a longer arrow. I need to have, I'll draw it over here. Drawing it over here, I have more force towards the center than I do gravity. All right, so continuing on with solving our problem, we're going to set up our sum of the forces equation as usual, right? So I have force of gravity plus the normal force. I'm looking for the normal force, so I'm eventually going to be solving for this. And this is going to be equal to mass times acceleration. But am I going in a straight line? I'm not going in a straight line. So this is actually going to be mass times my centripetal acceleration. All right, continuing on. So I'm going to start doing some substitutions now. Always do substitutions before you rearrange the equation. Reason being is that I need to make sure that I preserve the sign on these forces. So this is going to be negative mass times acceleration. if this was balanced, this would be positive, this should be negative mass times gravity. Oh, big difference here. And this should be something greater than that, just to do a reality check at the end. All right, so I'm going to have negative mg plus my normal force is equal to mass times the centripetal acceleration, which is v squared over r. And I need to solve for my normal force. So this is going to be mv squared over r plus mg. G is positive here. Now, remember how I said that my normal force needs to be more than mass times gravity? Look, I have a term plus mass times gravity. So this means that my normal force is going to be bigger. This, because I have a square term here, this can't possibly be negative. All right. And then lastly, continuing, I'm going to actually plug in my numbers here. So this is going to be 65 kilograms times, what do they do? They're going up 20 meters per second. Square that. Divided by 30 meters plus kilograms times positive 9.8 meters per second squared. All right, and then plug in my numbers, do some math. All right, and I did the math. I didn't check to see if this is right. I got 1503 newtons. Now, just thinking to myself, is this larger than the force of gravity? Force of gravity over here should be 65 times negative 9.8, which is 637. So what this says is that the normal force is going to be pressing much, much harder than the usual force of gravity. So this is something that would make you feel really heavy when you're going through this turn, right? Because usually the normal force that you feel is equal to your weight. So you would usually, on flat ground, standing still, feel a weight, or feel the normal force of 637 newtons. Now you're feeling like extra, extra large normal force. So this is going to make you feel really heavy, which is why sometimes you feel like your stomach is like sinking on a roller coaster. Just for fun, let's look at what this free body diagram would look like if you were going over the top of a roller coaster instead. I'm not going to solve a problem like this, but there is one on your worksheet. So if I were to do one where I have a roller coaster going over a hill on a roller coaster, all right, what are they doing? They're going like that. So now, if I were to draw in the rest of my circle, the centripetal force, or the net force, has to be down, right? So my centripetal force is going to be that way, and my centripetal force is going to be that way. And this is equal to the net force. So all three of these things are towards the center of the circle, which in this case is down. Now, when I do my free body diagram for this, this is going to look like I have I have the force of gravity going down, which is equal to negative mg. All right. Now, I could say maybe there's some other force pulling me towards the center, but that's not really how like roads and roller coaster tracks work. Instead, the way they work is that you have to be like you have the normal force. Imagine you're going over like a speed bump or something. There's nothing else that can pull you towards the center. So it's not like there's something pulling you in. Instead, what it is that you just have less normal force now. So you still have a normal force that's preventing you from falling through the track, but it's going to look like this. All right, so I need to have excess force excess centripetal force towards the center for this. So when I do this, I'm going to have my net force is going to be equal to the normal force plus the force of gravity, and that's still going to equal mass times centripetal acceleration, which is mv squared over r. Now, however, this acceleration is going to be down. So when I do this, my normal force is going to be a smaller number than the force of gravity. All right, so it's super important on these to make sure that you're keeping track of your signs, so good luck.